however, is not necessarily lower than that having valves. In fact, many fluid dynamical systems in nature and engineering more or less rely upon valvulus pumping to transport the working fluids therein. For instance, blood circulation in the cardiovascular system is maintained to some extent even when the heart's valves fail. Meanwhile, the embryonic vertebrate heart begins pumping blood long before the development of discernible chambers and valves. In microfluidics, valvulus impedance pumps have been fabricated, and are expected to be particularly suitable for handling sensitive biofluids. Inkjet printers operating on the piezoelectric transducer principle also use valvulus pumping. The pump chamber is emptied through the printing jet due to reduced flow impedance in that direction and refilled by capillary action. Pump repairs. Examining pump repair records and mean time between failures, MTBF, is of great importance to responsible and conscientious pump users. In view of that fact, the preface to the 2006 Pump User's Handbook alludes to pump failure statistics. For the sake of convenience, these failure statistics often are translated into MTBF, in this case, installed life before failure. 32. In early 2005, Gordon Buck, John Crane Incorporated's chief engineer for field operations in Baton Rouge, Louisiana, examined the repair records for a number of refinery and chemical plants to obtain meaningful reliability data for centrifugal pumps. A total of 15 operating plants having nearly 15,000 pumps were included in the survey. The smallest of these plants had about 100 pumps, several plants had over 2,000. All facilities were located in the United States. In addition, considered as new, others as renewed and still. Derelict windmill connected to water pump with water storage tank in foreground, others as established. Many of these plants, but not all, had an alliance arrangement with John Crane. In some cases, the alliance contract included having a John Crane Incorporated technician or engineer on site to coordinate various aspects of the program. Not all plants are refineries, however, and different results occur so. In chemical plants, pumps have historically been throwaway items as chemical attack limits life. Things have improved in recent years, but the somewhat restricted space available in old tin and asthma standardized stuffing boxes places limits on the type of seal that fits. Unless the pump user upgrades the seal chamber, the pump only accommodates more compact and simple versions. Without this upgrading, lifetimes in chemical installations are generally around 50 to 60% of their finery values. Unscheduled maintenance is often one of the most significant costs of ownership, and failures of mechanical seals and bearings are among the major causes. Keep in mind the potential value of selecting pumps that cost more initially, but last much longer between repairs. The MTBF of a better pump may bond to 4 years longer than that of its non-upgraded counterpart. Consider that published average values of avoided pump failures range from $2,600 to $12,000. This does not include lost opportunity costs. 1 pump fire occurs per 1,000 failures. Having fewer pump failures means having fewer destructive pump fires. As has been noted, a typical pump failure, based on actual year 2002 reports, costs $5,000 on average. This includes costs for material, parts, labor and overhead. Extending a pump's MTBF from 12 to 18 months would save $1,667 per year, which might be greater than the cost to upgrade the centrifugal pump's reliability. 32. 1. 33. Applications. Metering pump for gasoline and additives. Pumps are used throughout society for a variety of purposes. Early applications includes the use of the windmill or water mill to pump water. Today, the pump is used for irrigation, water supply, gasoline supply, air conditioning systems, refrigeration, usually called a compressor, chemical movement, sewage movement, flood control, marine services, etc. Because of the wide variety of applications, pumps have a plethora of shapes and sizes, from very large to very small, from handling gas to handling liquid, from high pressure to low pressure, and from high volume to low volume. Priming a pump. Typically, a liquid pump can't simply draw air. The feed line of the pump and the internal body surrounding the pumping mechanism must first be filled with the liquid that requires pumping. An operator must introduce liquid into the system to initiate the pumping. This is called priming the pump. Loss of prime is usually due to ingestion of air into the pump. The clearances and displacement ratios in pumps for liquids, whether thin or more viscous, usually cannot displace air due to its compressibility. This is the case with most velocity, rotor dynamic pumps, for example, centrifugal pumps. For such pumps, the position of the pump should always be lower than the suction point. If not, the pump should be manually filled with liquid, or a secondary pump should be used until all air is removed from the suction line and the pump casing. Positive displacement pumps, however, tend to have sufficiently tight sealing between the moving parts of the casing or housing of the pump that they can be described as self-priming. Such pumps can also serve as priming pumps, so called when they are used to fulfill that need for other pumps in lieu of action taken by a human operator. Pumps as public water supplies. Arabic depiction of a piston pump, Biljazari, c. 1206. 34, 35. First European depiction of a piston pump, by Takala, c. 1450. 36. One sort of pump once common worldwide was a hand-powered water pump, or pitcher pump. It was commonly installed over community water wells in the days before piped water supplies. In parts of the British Isles, it was often called the parish pump. Though such community pumps are no longer common, people still use the expression parish pump to describe a place or forum where matters of local interest are discussed. 37. Because water from pitcher pumps is drawn directly from the soil, it is more prone to contamination. If such water is not filtered and purified, consumption of it might lead to gastrointestinal or other waterborne diseases. A notorious case is the 1854 Broad Street cholera outbreak. At the time it was not known how cholera was transmitted, but physician John Snow suspected contaminated water and had the handle of the public pump he suspected removed. The outbreak then subsided. Modern hand-operated community pumps are considered the most sustainable low-cost option for safe water supply in resource-poor settings, often in rural areas in developing countries. A hand pump opens access to deeper groundwater that is often not polluted and also improves the safety of a well by protecting the water source from contaminated buckets. Pumps such as the Afridov pump are designed to be cheap to build and install, and easy to maintain with simple parts. However, scarcity of spare parts for these type of pumps in some regions of Africa has diminished their utility for those areas. Sealing multiphase pumping applications. Multiphase pumping applications, also referred to as triphase, have grown due to increased oil drilling activity. In addition, the economics of multiphase production is attractive to upstream operations as it leads to simpler, smaller in-field installations, reduced equipment costs and improved production rates. In essence, the multiphase pump can accommodate all fluid stream properties with one piece of equipment which has a smaller footprint. Often, Two smaller multiphase pumps are installed in series rather than having just one massive pump. Irrigation is underway by pump-enabled extraction directly from the guntie, seen in the background, in Kumila, Bangladesh. For midstream and upstream operations, multiphase pumps can be located onshore or offshore and can be connected to single or multiple wellheads. Basically, multiphase pumps are used to transport the untreated flow stream produced from oil wells to downstream processes or gathering facilities. This means that pump may handle a flow stream, well stream, from 100% gas to 100% liquid and every imaginable combination in between. The flow stream can also contain abrasives such as sand and dirt. Multiphase pumps are designed to operate under changing or fluctuating process conditions. Multiphase pumping also helps eliminate emissions of greenhouse gases as operators strive to minimize the flaring of gas and the venting of tanks where possible. 38. Types and features of multiphase pumps. Helicoaxial, centrifugal. A rotodynamic pump with one single shaft that requires two mechanical seals. This pump uses an open-type axial impeller. It is often called a Poseidon pump, and can be described as a cross between an axial compressor and a centrifugal pump. Twin screw, positive displacement. The twin screw pump is constructed of two intermeshing screws that move the pumped fluid. Twin screw pumps are often used when pumping conditions contain high gas volume fractions and fluctuating inlet conditions. Four mechanical seals are required to seal the two shafts. Progressive cavity, positive displacement. When the pumping application is not suited to a centrifugal pump, a progressive cavity pump is used instead. 39. Progressive cavity pumps are single screw types typically used in shallow wells or at pea surface. This pump is mainly used on surface applications where the pumped fluid may contain a considerable amount of solids such as sand and dirt. The volumetric efficiency and mechanical efficiency of a progressive cavity pump increases as the viscosity of the liquid does. 39. Electric submersible, centrifugal. These pumps are basically multi-stage centrifugal pumps and are widely used in oil well applications as a method for artificial lift. These pumps are usually specified when the pumped fluid is mainly liquid. Buffer tank. A buffer tank is often installed upstream of the pump suction nozzle in case of a slug flow. The buffer tank breaks the energy of the liquid slug, smooths any fluctuations in the incoming flow and acts as a trap. As the name indicates, multiphase pumps and their mechanical seals can encounter a large variation in service conditions such as changing process fluid composition, temperature variations, high and low operating pressures and exposure to abrasive forward/erosive media. The challenge is selecting the appropriate mechanical seal arrangement and support system to ensure maximized seal life and its overall effectiveness. 38, 40, 41. Specifications. Pumps are commonly rated by horsepower, volumetric flow rate, outlet pressure in meters, or feet, of head inlet suction in suction feet, or meters, of head. The head can be simplified as the number of feet or meters pump can raise or lower a column of water at atmospheric pressure. From an initial design point of view, engineers often use a quantity termed the specific speed to identify the most suitable pump type for a particular combination of flow rate and head. Pumping power. The power imparted into a fluid increases the energy of the fluid per unit volume. Thus the power relationship is between the conversion of the mechanical energy of the pump mechanism and the fluid elements within the pump. In general, this is governed by a series of simultaneous differential equations known as the Navier-Stokes equations. However, a more simple equation relating only the different energies in the fluid, known as Bernoulli's equation, can be used. Hence the power, P, required by the pump, where P is the change in total pressure between the inlet and outlet, in Pa, and Q, the volume flow rate of fluid, is given in M3/S. The total pressure may have gravitational, static pressure and kinetic energy components, i.e. energy is distributed between change in the fluid's gravitational potential energy, going up or downhill, change in velocity, or change in static pressure. Eta is the pump efficiency, and may be given by the manufacturer's information, such as in the form of a pump curve, and is typically derived from either fluid dynamics simulation, i.e. solutions to the Navier-Stokes for the particular pump geometry, or by testing. The efficiency of the pump depends upon the pump's configuration and operating conditions, such as rotational speed, fluid density and viscosity, etc. For a typical pumping configuration, the work is imparted on the fluid, and is thus positive. For the fluid imparting the work on the pump, i.e. a turbine, the work is negative. Power required to drive the pump is determined by dividing the output power by the pump efficiency. Furthermore, this definition encompasses pumps with no moving parts, such as a siphon. Efficiency. Pump efficiency is defined as the ratio of the power imparted on the fluid by the pump in relation to the power supplied to drive the pump. Its value is not fixed for a given pump. Efficiency is a function of the discharge and therefore also operating head. For centrifugal pumps, the efficiency tends to increase with flow rate up to a point midway through the operating range, peak efficiency or best efficiency point, BEP, and then declines as flow rates rise further. Pump performance data such as this is usually supplied by the manufacturer before pump selection. Pump efficiencies tend to decline over time due to wear, E.G. increasing clearances as impellers reduce in size. When a system includes a centrifugal pump, an important design issue is matching the head loss flow characteristic with the pump so that it operates at or close to the point of its maximum efficiency. Pump efficiency is an important aspect and pumps should be regularly tested. Thermodynamic pump testing is one method. Minimum flow protection. Most large pumps have a minimum flow requirement below which the pump may be damaged by overheating, impeller wear, vibration, seal failure, drive shaft damage or poor performance. 42. A minimum flow protection system ensures that the pump is not operated below the minimum flow rate. The system protects the pump even if it is shut-in or dead-headed, that is, if the discharge line is completely closed. 43. The simplest minimum flow system is a pipe running from the pump discharge line back to the suction line. This line is fitted with an orifice plate sized to allow the pump minimum flow to pass. 44. The arrangement ensures that the minimum flow is maintained, although it is wasteful as it recycles fluid even when the flow through the pump exceeds the minimum flow. Schematic of pump minimum flow protection arrangement. A more sophisticated, but more costly, system, see diagram, comprises a flow measuring device, FE. In the pump discharge UHIC provides a signal into a flow controller, FIC, which actuates a flow control valve, FCV, in the recycle line. If the measured flow exceeds the minimum flow, then the FCV is closed. If the measured flow falls below the minimum flow, the FCV opens to maintain the minimum flow rate. 42. As the fluids are recycled, the kinetic energy of the pump increases temperature of the fluid. For many pumps, this added heat energy is dissipated through the pipe work. However, for large industrial pumps, such as oil pipeline pumps, a recycle cooler is provided in the recycle line to cool fluids to the normal suction temperature. 45. Alternatively, the recycled fluids may be returned to upstream of the export cooler in an oil refinery, oil terminal, or offshore installation. References: 1. Submersible slurry pumps in high demand.
We're not going to read that, and the video has